chapter. So, title chapter name Refraction through lens. The previous chapter, it was again refraction, but the concept was we were taking plane surfaces, like we were taking a glass slab, the front end of pyramid, a prism that will be either equilateral prism or maybe a right angle prism. Okay, so all these were plane surfaces. They were not having any curved path to it. All the sides were straight lines, you can see. And this chapter, we will be discussing lens, which is having some curved surfaces along with it. So, how does refraction of light happens through these curved surfaces? This is what we're going to be doing in this chapter. So, today is just the intro part. Basics, we need to know the names and few terms required for solving numericals and for also doing diagrams. Okay, so in your notebook, you can write types of lenses. In ninth grade, you already, everybody has done reflection of light where we have taken concave mirror, that is mirror concept, and this is lens. Who can tell me what is this mirror called as?
Oh, mom, I can't see the screen.
Screen is not visible
I
to
can't see
anyone.
it.
Okay. Yes, Anushka, if you are able to see the screen.
Yes, ma'am.
Okay, so having any screen issues, you can try to rejoin. If it's the same for all, then there is a problem, or else try to rejoin your meeting.
Okay.
Okay, who's going to tell me which type of mirror is this? Is it concave or convex? This one. You have to see the,
Convex.
mm, it is a convex mirror, correct. You have to see the painted portion, the portion which has been painted. Painted is just to give a polishing. The free part of it is a bulged part. So bulged one is a convex mirror. So this is a convex mirror. And if same thing I would have taken and the bulged part is polished and the internal part is free, then this is an example of concave mirror, which you have done in your ninth grade. Okay, so mirrors we are not going to take, but something like similar to this is what lenses are going to be. So lenses are going to work in a similar manner, but there are types of lenses first we will see, and we will only focus on the two basic types. So when you have curve like this on both the part, it is bulged. Okay, it is bulged at both the part. So you can see that this left curved part is actually belonging to a spherical mirror which falls on the right end. Okay, this is for the left region, the left curve region. I'll mark that with a red color so that you understand that while we discuss for lens, we're actually taking two spherical mirrors. So this red region is a part of a spherical mirror that falls on the right side. Okay. So if I remove the other end, it forms a proper circle and the circle will have a center. The circle will have a radius. Okay. And if I take the other end of this lens, the other end belongs to a spherical circle that falls on the left side. Okay, the black one is a part of a spherical circle or mirror that falls on the left side. Okay, so when you discuss lens, it is never, of course, one spherical thing can have two pieces which you can combine. So lens is definitely part of two separate spherical mirrors. Okay, we do not draw the remaining circles, but you can understand if I'm just discussing the black part, the center falls on the left side. So there will be a center on the left side as well, and the radius, which will be R. If I'm saying this is C1 and R1, there will be C2 and R2. So a lens will have two center of curvatures, and it will have two focus, it will have two radius of curvature. Okay, so you can see the same thing if you're taking the other lenses. So if I'm taking a lens like this, we will see the names of these lenses. Now, this curve portion that we have, this right side portion that we have, belongs to a spherical mirror that falls on the right side. And this left side curve is a part of a spherical mirror that falls on the left side. So this is also part of two spherical surfaces that we have. Okay. So this is C1 if I want to call, and I will call this as C2. And same thing, I will have radius R2, radius R1, and these are the two prime lenses we will be studying. So we are not going to be doing that extended part. We'll directly come to the names and the types of lens. Okay. So what you see here, it is, if I just remove one part, okay, and let's say the internal part is packed, this left end is open and it works like a convex lens. And same thing to the other end, I'm attaching a similar, sorry, convex mirror, and I'm attaching a other convex part to it. Okay, so these are the two opening ends which are free for refraction. So these together, because left side and right side both are convex, correctly you will call this as biconvex lens. It's a lens. Okay, but in our textbooks and all, we will directly refer this as convex lens by default. When I say convex lens, this is the lens that you should be drawing. Okay, but you should know the proper name of this is biconvex because on both the side it is having that convex structure. Now this one that you have both part or both the left and the right side concave. Okay, so this should be called as biconcave lens. Shortly, in all our textbooks, we refer this kind of lens as concave lens. That's the figure for convex and this is the figure for concave lens. We do have other lenses. We just know the names of it. We're not going to be using that, but at least we should know the names. Okay. If I may draw one straight path, no curve, and to the right end, it's a concave structure. This is straight, plane, and this is concave. So you will call this kind of lens as plano because one side is plane, you will do the reading this way. And the other is a concave part, so it's a plano concave, or you can also call that as concavo lens. Okay, so can you guess the name of the other lens that I'm drawing here? It's straight like this and a D shape like this. What should be the name of this lens? Yes, the hint part is here. What should be the name of this lens? One is straight and the other is bulged. Yes, Nidhi, what should you
Plain or
call this lens?
concave?
Correct. Not concave, it is convex. There's a bulge part open, right? So it will be plano convexo lens or plano convex also you can write. Okay. So these are all the extra, but of course you do not have these in your syllabus to do, but naming is yes required. Okay. The first and the third figure. This is what we'll be using throughout our concepts. Yes, done with the figures. You can draw this down quickly, everyone. Write their names. Yes. Can you guess the lens which is of this type, like a crescent moon? What should you call this as? Yes, this kind of structure. See two parts of the lens always. The left part is a bulged and the right part is curved inside. So what should you call this kind of lens as? Yes, who can tell me
Concave
the
or
name of this?
convex.
Well, it is going to be concave or convex. I think this is one of the question there in your, if you're referring Selena book, do have this question. It's not really peak, it's having a little thickness at the top and the end. Okay, finished with the diagrams, everybody. Now, if I may ask you about the thickness, we are focusing on the first and the third, as I said. The thickness at the center for both the lens which we are going to be studying. How can you define the thickness of lens when you're taking these two types? Which one is thicker at the center part? Yes, and it's not going to be this fat. This is just for the diagram purpose. All the concepts we are doing later on, it will be considered for a very thin convex lens and concave lens. It's not going to be very thick as that you can see it on the screen. Okay, which one is going to be thicker at the center part? Let's say we cut down this portion like this. This forms the center part. So whenever you have convex lens, it's thicker at the center. And as you move upward or downward, it tapers. That means it is going to become thinner and pointed. Okay. At the two end, you will see it tapers and is thinner. Both the end. Okay. While we discuss for the concave lens, you will notice at the center it is thin. Okay. And as you go towards the end, it diverges and it is thicker as compared to its own center. And it expands. It's not tapering. Tapering is trying to come to a point. So this is diverging. It's going outward. Okay, so this is the way we identify. These are very basic things that we should know about convex lens and concave lens. Okay, this point is clear. Any doubt in this? This is very simple things. Okay, now if I may give you this first structure and the way I have divided it, there is a question that they do ask, especially from the convex part. Okay, they will ask you take this and divide it horizontally. The pieces you're going to uh, get, are they going to be similar to any other plane surfaces you have studied from your fourth chapter? So they do give you this, and the way you're going to cut down is between these two divisions. You get almost the first piece like this, second piece almost this, and the last piece like this. So you will be saying the center part will work like a glass slab, and the top and the bottom one will work like prisms. Okay, so draw this section and also show the splitting, how you have divided it. If you cut it down, and this is applicable only if you're taking very thin convex lens. For very thick convex lens, you will still have that curve part. If it's a very thin one, this curve part is almost negligible when you cut the pieces of it. Okay, so draw this quickly. Write the two plane surfaces we're going to get there. Done with the diagram, then tell me. Yes, finish everything and drawing everybody. Is there anyone who's still drawing any part? Okay, now we can directly come to the rules. A few things which you've done in your previous grade regarding the focus and the focal length, center of curvature. Similar things will also be used here. So today we'll just do the basic points related to the lens. Okay, whenever you do the structures or whenever you do the numericals, okay, you have certain rules which are similar to both of them, and some of it will be differing when you're taking convex lens or when you're taking concave lens. Okay, now roughly you can draw it for the time being. And if you want to do it with measurements, how you are supposed to draw this lens is whatever is your page, and you want to make your lens here. You want to draw your lens here. Okay. So what you need to do is wherever is the line of the book that you're referring will have lines. Never do the points on the line because whenever you want to draw the principal axis, it will be going over that line. So always try to do one thing. Wherever are the two lines you will find for your books, somewhere in the middle you are supposed to place your compass. Okay, and the thickness is what you will decide. So if you're taking around, let's say, 3 centimeter, place your compass here and draw an arc which will be, and 3 centimeter will be too big for your book. 2.5 is fine. I think 2 or 2.5 you can take this much centimeter. Draw an arc like this. Okay. So one part will be done. Then thickness will be decided by you, but make sure you are going to place the compass on the same line that you have placed the first position. You can shift your compass to the right side and do not make changes to this measurement. 2.5, keep it as it is. Suppose I'm going to place it over here. Okay, little, at least try that wherever is your curve, shift your compass little to the right end and make sure you're taking the double of it for this compass marking. Okay, and then double of 2.5 is going to be 5 centimeter. Keep your compass here and make the second cut. So whatever cut you're going to get, the extra part you can erase and you will get your convex lens. Okay, so this way you're going to be making your convex lens. Same way you can take for concave. So for concave, what you need to do, wherever are the lines is set, you place here 2.5 you're taking, make a cut, extend it from this point wherever is 5 centimeter, and then the thickness is always decided by, if you're fixing it to 2.5, then exactly the double of it, and take your, to the left side you're going to make that cut with a gap and try to connect it, but do not try to make it too thick. This way you can do with proper measurement. For now you can just try with rough way just to understand the rules. Okay, so first rule, you all know there is a straight horizontal line over which all the diagrams are referred. All your object and image and all of that things come over this line. So it is that line, very important line, termed as the principal axis. Now, can anyone tell me for this lens how many focus will be there? For this lens, how many focus technically you're going to have? We have discussed at the right beginning. One curve is belonging to another circle part, and the right side is going to belong to a left circle part. So there will be two centers, two focuses. Okay. So if let me say this is C one. Actually, this has to be taken the second. I'm just taking this C1 and this is C2. So between the center, now this center is taken from optical center of your lens. So there is another center for your lens, and this is going to be falling. See, if you take a very thin one, and for 10th base concepts, we are taking that this center falls exactly on the geometric center of this lens. If it is thicker, or maybe the radiuses are not the same, then it's not necessary that the optical center will be coming exactly at the geometric center. There are two center, geometric center and one is optical center. Geometric structure center is what you have drawn. That's your geometrical figure, and it will have its own center called as the geometric center. Okay. This is valid for all the textbooks that we are referring for 10th, that the geometric center is where your optical center for the lens will also lie. So for now, we can just refer this as a center point for the lens. This is called as your optical center for the lens. And from this optical center, this point you have taken, C1, this whole point will be referred as radius of curvature, which you can refer as R1 because it's C1, you will write R1. Like that, from the optical center to this point, this whole path will be called as radius of curvature R2. Then C1 and optical center will have a center point, midpoint you can say. That midpoint is called as the focal focus or the focal point. So because this is C1, this is going to be F1, and between these two, there will be the center point as F2, focus 2. So there will be two focus, there will be two center of curvature. But that is just for the convention of diagrams. They do have their own way to define. Now, whenever you're going to take convex lens, there are two focus. So which focus should you write while you do your numericals? Should you take focus 2? Should you take focus 1? So whenever you are discussing for convex, you can write it down. These are the most confusing thing. This will be difficult if you do not know. When you do your diagrams and when you do numericals, this is where you will start finding difficulty. You can write all the points required for convex lens. Today we'll just focus on convex lens. So for convex lens, though there are two focuses and two center of curvature, you will be taking the one which is on the left side. So F2 is the focus. You will refer, and what is this F1? The one that is on the left side of the lens. That is the focus you will be considering when you're doing your numericals. Okay, now what is a focus? How you actually define focus? See, for simplicity, we do understand it's the midpoint between the center of curvature and optical center. But that's not the actual definition of focus. Focus is what? Whenever you try to, um, you know, make two lines parallel, which is okay. And also one more thing, always try to draw a dotted dash line which crosses over the optical center. Why this dotted line is important? Because some of the lines are going to get deviated when you're considering concave lens, and all these lines are always going to hit on this point. Okay, if you do not draw, never draw it straight and show diversion over here. Don't show bending and refraction at this point. Refraction, if you want to show, it will be touching at the centermost point, and then it is getting deviated. So that dotted line you should be drawing whenever you're considering the lenses. Yes. Done with the diagrams, everyone.
Yes, ma'am.
Okay. Now, before we proceed to the topic, we have uh, some rules that we need to do. Can you all tell me, whenever we are doing the reflection, what were the laws of reflection we studied? Laws of reflection. Yes. What were the laws of reflection we have studied? So for convex, how many of you remember the laws of reflection we've done? There were two laws. What were they?
Incidence is equal to angular reflection.
Correct. Angle of
And
incidence and angle of reflection are, yes, equal. And
and the um,
incident ray,
incident
the
ray,
reflected.
reflected ray, and normal lie on the same plane.
Correct. Yes, absolutely right. These three rays that you draw, normal is the perpendicular, incident ray, reflected ray, all of them they fall on the same surface, same plane. Okay, this was the law of reflection. Laws of refraction we have already done in the previous chapter. Okay, just make a change here. For convex lens that we're taking, focus has to be the second focus. Make that change. F1 we will take when we're taking concave lens. Here, take F2 as the focus, not the F1. Because the lines are going to come and diverge to the second focus. So as they hit here, okay, rules you will see, but I'm just telling you what focus are we going to take. These two lines are going to get diverted and they're going to meet at this point. Wherever the two lines are going to meet, what are the lines? First of all, they are parallel lines. They're mostly going to come from the left side. Now, many of you may have a doubt that why are we always drawing from left side? Is it not that ever that objects can be placed here and lights are coming from this side? Absolutely right. If you're drawing your objects on the right side, you're making your objects on the right side of the lens, then the rays are going to come to this end and then it's going to meet on that side. Okay. So it depends on where you're placing your object. Just for convention, we are just keeping it on the left side. All the books that you are referring for your 9th and 10th and even 11th, 12th, 12th, you have ray optics chapter. So this is again going to be used in your higher grades. For all the simplicity, we are keeping the object on the left side. It is not that objects are always on the left side. It's only for our convention. But then all the rules that you're doing for your textbooks, it will change. If you're taking things on right side, reverse all the signs then accordingly. Okay, but do not get it more complicated. We can always keep it on the left side for our study. So object is kept on the left side. My first question is, where is this object kept such that the rays are coming parallel from it? What do you think? Where is this object placed?
Ma'am,
Every
is it
line has its own. Is it at?
infinity, like not at
Correct.
directly?
Yes. Yes. When objects are placed at infinity. Now, this infinity is not an infinity for humans. It's infinity for the lens. Lens may be very small, and a distance which is few kilometers will be infinity, or few meters from that place will be infinity for the lens. So, if I'm saying I have this thing, infinity does not mean something coming from another galaxy. Okay, lights coming from other system or from other constellation path. No, infinity is according to this lens. Lens is if it is small, if it's big, of course. Now, if you see the lens we're using for the solar trapping, like the solar energy trapping, those are like very big lens, correct? For them, the infinity will be anything which is few kilometers away and it's able to trap the sunlight. And sunlight, it's not trapping the actual sun's light. It's trapping the light which is almost reached till the atmosphere. And from there it is trapping. It's not directly trapping from sun because that's the size of it. So size of the lens, according to that, infinity is a far distance which is few meters or kilometers depending on the size of it. So if object is kept at a far distance, light falling on the lens will always be parallel. Now you need to have two minimum rays, which we have I think already discussed. If you remember the pond question of fish and the plant and the bird that we have taken, I've told you always two minimum rays has to be there. You can draw more than that, but it will make a clutter on your diagram. So it's better just take two rays, one on the top, one at the bottom. If it is coming from infinity, all these small little things you have to notice. If it is coming from infinity, try to make one line coming to the bottom portion of the principal axis because it's a big object. And with a big object kept at infinity and light is actually coming from that and falling on it means the size of that object will be big enough. Okay. If it's a very tiny object kept at infinity, tiny object will not be having such kind that it will be able to take the light falling on it and it will come and try to fall on the lens. So always remember 2 points. Rays coming parallel are always kept at infinity. Size of that object is much, much bigger, very big. Such big that at least two or more rays are able to fall on it. So one you will take it on the top, one to the bottom of your principal axis. These two rays will hit onto your lens. Now, what is the phenomenon that will happen is actually refraction. But always remember, practically it is not total refraction. Few of the lights, I may use a blue line here. Some of the lights do get reflected. Few of them, depending on how many rays you have made, few of the lights can get reflected back. Okay, so part of it gets reflected. Major part of it will getting refracted, but the reflected part we are not showing it. Okay, in your diagrams it's not necessary, but always understand few light do get reflected back. Part of it, the remaining one will get reflected. So they will enter into the lens, and wherever you have drawn that straight line passing through the optical center, you have to make it travel till that point, and then from there you will show the deviation. Okay, so it is going to meet at a point. Now, the point that it meets, if it is parallel, it will meet exactly at a point, and that point is called as the focus. So, for the this convex lens, which focus is this? Are these two rays meeting? It is the second focus. So, when you do your numerical, you will be considering the second focus while solving your sums. Okay. Now, mostly sometimes they can also fall below the focus, above the focus, but usually the rays are always going to fall within this same plane. It can be up, down, exactly on the principal. So, somewhere on this range, this plane is called as the focal plane. Okay. Not necessary exactly it will be on the principal axis, whichever possibilities are there. Principal axis is one such case where lights coming from infinity will fall on this, that is for sure. But chances if anytime up and down it gets shifted, so maximum what is the range within the lights can meet, that range will be called as the focal plane. It will not fall out of it. Okay, so that's the first thing. So this is how we define focus. What is focus? When parallel rays fall on the convex lens after refracting. Okay, there is this refraction you have to use. After refraction, they emerge out and meet at a point, and that point is called as focus. So just for our understanding, we say, okay, it's the center point between the optical center and center of curvature. The middle point is focus. But that's not how you should write. You will be writing that when the rays, parallel rays, uh, is falling on the convex lens, after refraction, they will emerge out and meet at a point, and that point is called as focus. Okay, I'm not giving you definition. For that, notes will be given because we need to do a lot of practice for the ray diagram and the numerical. So notes will be provided to you. You will, and I will tell you every day which how many parts we have covered, so that you can start writing your notes. Okay, like I may give you that PDF first 2 pages have been covered or whatever has topic is done. You're going to write that into your notebook. Okay, so definitions this time I'm not giving it to you during the live class. We will try to focus on the concepts and we will be trying to do the numericals. Okay, now coming to the second lens. If anyone wants to draw or write any point, you can quickly write. I'm giving you time for that. Then we come to the focus for the other lens. Let's finish writing. Everyone, anyone is writing any point? Okay, done writing. Now, same length I'm taking, and this time be careful how the rays of light are emerging out. So I have the same lens, convex lens, and this is the principal axis. Principal axis connects the C1 and C2 and even optical center. So line that connects all the three will be called as the principal axis. It's a horizontal line. Okay, if I take focus here, F1 and F2, okay. So if I'm considering the first focus, light is coming, so light will be coming from this part, correct? If the light is coming from the focus, like I've actually placed the object exactly at focus, very tiny object, and the rays of light is going to emerge out like this. Okay, many lights you can, many rays you can draw. Many rays are coming out if you want, but as I said, plenty of rays will just make it little shabby when you do your diagrams. So as it hits, it comes out straight. Okay, it gets refracted straight. So it's just the reverse what we have studied. Okay, when rays were coming parallel, they were falling on the second focus. Here, the rays is coming from the focus. It's coming out like this. Okay, diverging out like this, and then it goes parallel. So this is also a valid figure, but you have to be careful how the rays of light was taken. Initially, when it was kept at infinity, it was coming parallel. They all converge to meet at second focus. Okay. Here, the lights are coming from the focus, and after refraction, they will all travel parallel. Now, if I may ask you, if the rays are traveling parallel, where will they meet? Where are they meeting? These are the rays which is going and getting these are the one that is falling on the lens. So these are the rays coming out of the lens. So if rays are parallel, are they ever going to intersect each other? Are they ever going to meet each other? Yes. Do parallel rays meet each other? Yes or no? They do not. So then where is the image formed? So we will use the reverse concept. We understood rays coming from infinity are parallel. So apply the same converse concept that rays which is emerging out, and these rays are all parallel. If they are parallel, they will meet at infinity at a very far distance. Okay, so two things you can all quickly write down. One is rays coming from infinity are parallel to each other, and rays emerging out, it can be, for now we will understand that not every ray will be same for convex and concave. So emerging out after refraction that are parallel will meet at infinity. Okay, so write these two information. Okay, okay, done writing everyone. Now, so in most of the cases, by default, the kind of lens we are discussing These are called as equiconvex lens. And if you're taking the other one, okay, these one that we will discuss will be called as equiconcave lens. Why so? Because in both the cases, the radius, there are two radius of curvature I told you, one on the left side, one on the right side. So radius of curvatures will be equal. The two radius of curvatures we have, they are equal. And if they are equal, then such lens will be called as equiconcave or equiconvex. As I already told you, optical center need not be necessary at the center point. Okay, it will be falling at the geometric center only if your radiuses are equal. If the two radius are equal, then it's these types of convex lens and concave lens we are discussing, and only then the optical center will be lying exactly on the geometrical center of your lens. Yes, that means if your radiuses are not same, the left side is little, to the left, like this, it might be little less bulged, and the other one is a little more bulged. It looks like a convex lens, but this bulge that you see, it's more flat over the left side and more bulged on the right side. It is convex, but it is not equiconvex, which you can see it is not equally distributed. The radiuses on the left and the right side are not same. In such cases, I can't see that this line I am trying to connect, the top portion, that is the vertex on the top and the vertex at the bottom. That's how we are doing the geometrical center. That is the apex part, the top and the bottom part, and draw straight line, and this is going to be the center. But you can see and you can notice that when you have this smaller and this little bulged out, and if you try to connect the top and bottom portion, it's not necessary optical center will be here. Optical center might get little shifted to the right side also. So it depends on the radius. Radius of curvature plays a very important role. If that is not equal, your optical center will not be the same. It might get shifted to left or to the bottom, mostly to the right and left, depending on where it is more bulged. Okay, done writing all these points. Now, as I told you, radius of curvature is so important. My question to you is, if I take this lens, right now we're only discussing the convex lens. Okay, if I have this convex lens, it will have its own focal length, correct? We think it's fixed. That means it's a principal axis I have, and I have, let's say, C1, F1, and O, and here we have F2 and C2. How do you calculate focal length? Very first question. How do you calculate focal length? Yes, anyone can tell me that point? How do you calculate the focal length? In mirrors, how did you calculate it? Yes, how do you, this is focus, or you can call this as the focus point. But what is focal length? How do you calculate that? You calculate it now by simple definition. It's from the optical center. This is your optical center. From there, this length. Let me make it bold, black. This distance that you see, that's the focal length. If you're taking the left side focus, then from this center to the left side, this path will be taken as the focal length. That is by definition. That means if I have a lens, and these are the points I've told you, this is focus, this is center of curvature, this is optical center. If I'm taking it in air or if I'm taking another medium, my question is, will the focal length change? If I take the same lens and I put it in water, okay, this is lens. Lens is made up of some material. Yes, lens is made up of some glass material. And just before this, we have done the refraction chapter. Glass have its own refraction. It's a material, and every material has its own refractive index. So glass has its own refractive index. Right now, it is in air. I take this lens and I put it in water. Okay. Yes. So Anushka, answer. Will the focal length change? I put it in water. Will the focal length change for the lens? Yes.
Yes,
What is the reason?
because the refractive index will change.
Correct. That is right. This material that is fixed. Of course, lens is not changing the material. Lens is made up of glass. It has its own refractive index. But yeah, we never discuss absolute refractive index. We always refer to mediums. Glass with respect to air. Glass with respect to water. Correct? Material is glass, that's fixed. But can you see the first, with what you are comparing? What is the surrounding? That has changed. Initially it was air, now it is water. So refractive index has changed. Why? Because we've changed the surrounding medium. Glass is fixed. Lens is made up of glass. It has its own refractive index. But because you have changed the medium, refractive index has changed. And if refractive index changes, focal length will change. And even radius of curvature. If you change radius of curvature, then also focal length is going to change. It's a very important question. Okay, you have to understand this. This is one of the most trickiest question to remember, and but we're doing all the questions simultaneously. Concept questions, I'm taking it as we're going with the chapter. So we do have these questions. When you take lens, it can be concave lens or convex lens. If you change the medium, if you put it in water, you put it in turpentine oil, you change the medium, put it in a transparent medium. The question is, will the focal length change? So yes, it will change because your refractive index has changed. Okay? Because glass is a fixed thing, but the surrounding medium you have taken, you have changed that medium. So the overall refractive index will give you different values. And that will directly impact your focal length. So focal length is never fixed. It can change. You can change it. Maybe yeah, one time the lens is made one time. You can't do anything with the dimension of the lens. But if you want to work with some, you want to change the image, you want to make some changes to the image, you want to work on with the focal length of it. If you change that, a lot will affect your image. So the only thing that is in your hand is you can change the medium and do that. Okay, so you can write this down. If the refractive index changes of lens with respect to medium. If the medium changes, okay? Whenever you're taking, mediums are changing. If the surrounding medium, if the surrounding medium has changed, then writing this part, then the refractive index will change and so the focal length. Okay, so write this down. Focal length of the lens. That will also change. Okay, done writing, everybody. Anyone is still writing any point? Yes, are they finished writing? Maybe Michelle, Ansh,
Yes, ma'am.
Anushka. Okay. There's some more interesting thing we'll see related to focal length. These are also the questions there which we're covering. And this question has come for some previous board exams. Now I have a convex lens like this, and I have covered, let's say, the top portion with a black cloth. I've covered it up. Okay, camouflaged it. Now my question is, will the focal length change? Because only half part of the lens is used. Will that imply the focal length will change? Will focal length become half or one fourth or something like that will happen to the focal length? Yes, I want everybody's opinion on this. Michelle, let's start with you. What do you think? If I cover the top portion with a black cloth or any cloth, basically I'm just covering it up. and only the bottom portion is available for refraction. So will the focal length change?
Yeah, I guess.
Okay. Adit, what do you think?
I also think so.
Okay. Anushka.
I'm not sure.
Okay. Ansh, what do you think?
No.
Okay. Nidhi?
No, it won't change.
Right. It will not change because focal length, this will change only under two parameters. One is the refractive index, and second is the radius of curvature. Nothing else will have any impact on the focal length. You use half part of a convex lens, one fourth part of a convex lens, be it any portion of a convex lens, the focal length will not get affected. Focal length will only get affected if you change the surrounding medium, that is, you're dealing with the refractive index. I may also ask you this. I have this made up of quartz glass and this one with ordinary glass. So, yes, in these two, I mean, size are same, dimensions are same. Let's say the width of it is same. But if these two are made up of different type of glass, they will both have different focal length because focal length depends on your refractive index. It deals with refractive index. If this factor changes, focal length will change. There are many factors on which RI changes, which we have done in a previous chapter. That's why that chapter was taken before. Because we studied the different factors on which RI depends. So do that factors, revise it, that will be utilized again in this chapter. And yes, the radius of curvature directly related to thickness also. Thickness is like if it's too thick or thin, that is also something you're dealing with radius of curvature. So you will write the first point. This question is clear, I hope, that if you're using half part of the convex lens will have no effect on the focal length. But yes, there is one more question I'm covering right now. If you have a thin convex lens and a thicker convex lens, okay, so they both will have same made up of same material. Material means Ri is something, but Ri also has to do with thickness. Okay, we have studied glass slab if you remember. If you have a thicker glass slab and a thinner, it will have an impact on the refractive index. So thickness affects the Ri, and thickness is also related to radius. So remember this thing and write this important point. If you have a thinner lens, focal length will be increased. Okay, they're opposite to each other. Thin one, more the focal length. And thicker one, this one, the second one is the thicker one. If you have a thick lens, it will have less focal length. That means focal length decreases or reduces. Very important point. Okay, so what all we have done, we've just done some questions based on convex lens, how it looks, how many types of focuses are there. We have done one rule about parallel lines meeting at a focal point, and if rays are coming from focal point, they're all diverging and they will all go parallel once after getting refracted. Then two, three questions we have covered under convex lens. Remember, focal length, be it of convex lens or concave lens, for both the factors are same, Ri and radius of curvature. You try to change any of this, you try to disturb either Ri, you can change the medium, you can make it thick or thin. These things you can work on with, right? So you are affecting these two factors, then the focal length will get directly impacted. That means if it is made once, does not mean it has a perfect dimension. It all has fixed focal length. You can always change the focal length by doing all these changes. And this last question was where you're taking thinner question are asked. Sometimes comparative questions are asked. If it is thin lens, it will have more focal length. If it is thicker, it will have less focal length. So you can always understand, like if I have a thick one, due to some reason, let's say this is the F2, okay, and I'll draw thinner one inside it. Okay, so let's see, I have a fixed focal point. This is a thinner one. For both of them, let's say the optical center is the same. So See this distance for the pink one from center to this. It's large as compared to, as if it is thicker, it will have this dimension, bigger dimension. Okay, it will have its own center and this distance will be less. So as you expand, the gap over here will become less. So thicker one will have less focal length and thinner one, if it is flat, it will have more gap and it will have more focal length. Okay, so revise up all the points we have discussed today. And as I've told you, revise the RI again with colors because we will be having that red color and blue color concepts, wavelength of it, frequency of it, and how division will affect. So I may give you a convex lens and ask you if two different rays of light are used. They will all have different bending, correct? So revise up that thing because that will be included in the questions for this chapter. Okay, so rest we will cover up next week. And notes will be sent to you today itself. As I've said, I'm not giving you any running notes for this chapter, the definitions and all that. It has plenty of definitions. So we'll not be investing a lot of time in writing those definitions. I'll mark and tell you what you all need to write. But as I told you for revision, you have to go through the RI concept and the color based concept from refraction through lens, through plane mirrors. Sorry. Okay. Pick up that, revise. That will be helpful when you do your next lecture for this. Okay, so we'll meet up then tomorrow.